Okay, hello. This is AMT 180 Aircraft Instrumentation. I'm going to begin lecture for September 8th. I see that there are a few people on here. The link is posted in Canvas. I'm going to turn off these lights so that we can see the slides. Okay, make sure you guys can do this well. Hello, Ken. Hello, Trin. Okay, so here we are again. We're going to continue talking about engine instruments. Can you guys see that? If you want to type in the chat. Is that viewable? Okay, good. Okay, so we're going to continue talking about engine instruments. Some of the engine instruments we're going to talk about today are considered engine condition instruments. So those instruments include engine oil pressure, which we've covered a lot already, engine oil temperature, which actually I'm not going to get into today. We're going to get into a little bit of the temperature instruments. Engine oil temperature is not one of them, though. We will talk about EGT, and we will talk about turbine outlet temperature and turbine inlet temperature. And then we also have engine instruments that are considered engine performance indicators, that being our RPM indicator, tachometer, and our manifold pressure indicator. We talked about manifold pressure in the last lecture, so we have covered that in detail. And RPM and tachometer we are going to cover in another lecture at a later time as well. So today we're going to go over more of the performance-based indicator, the condition-based indicators, and then in the lecture on Thursday, we will continue going over engine performance-based indicators and others. So engine instruments. It is essential that engine instruments, not just engine instruments, this kind of pertains to all instruments, but right now, since we're in the topic of engine instruments, it is essential that they be fitted properly to the aircraft and function correctly. This is the job of an AMT in regards to aircraft instruments. So that's what our whole class is about, right? Aircraft instruments and what we need to do with them. So our essential job as far as instruments go is that we need to make sure that all these instruments are fitted properly to the aircraft and function correctly. If not, that's when we can remove and replace. We do a little bit of troubleshooting, such as if we need to correct indicators for range markings, stuff like that, but we don't really do any troubleshooting as far as repairing the instrument itself. And we'll continue talking about pressure sensing instruments. We'll talk about all of the remainder of engine instruments that are pressure sensing today. So that list includes engine oil pressure, which we've discussed, manifold pressure we've discussed. Today we're going to talk about EPR, engine pressure ratio, fuel pressure, hydraulic pressure, vacuum pressure, and pressure switches. Starting with EPR, engine pressure ratio. So turbine engines have their own pressure indication that monitors the power being developed by the engine. And this is the engine pressure ratio gauge. That would be our indicator for the system. So the EPR gauge compares the total exhaust pressure to the pressure of the ram air at the inlet of the engine. The EPR gauge presents an indication of the thrust being developed by the engine. So this gives us a look at the condition of the engine, especially as far as it's concerned in turbine engines, gives us a condition based on what the thrust is looking like. And that gauge system has a system where it compares the exhaust pressure to the inlet pressure. The EPR gauge is a differential pressure gauge. That differential pressure being between the inlet air and the exhaust gas air. It's a remote sensing instrument. It receives its input from an engine pressure ratio transmitter. And in digital instruments, the display is often on a computer. Okay, so those are a couple of facts that we covered early on in this class. Remember, there's different kinds of pressure. This one is a differential pressure, and we also have remote sensing and direct reading. So this one is a remote sensing. In our EPR transmitter, the pressure ratio transmitter is a bellows arrangement. It compares the two pressures and converts the ratio into an electrical signal. So this system contains a transmitter in order to take that mechanical energy and convert it to an electrical signal to display in the cockpit. This is, am I going too fast for you guys? Sometimes I forget that you guys have to take notes, and it's not as easy to tell if you guys are doing that as it would be if we were in a classroom. Just let me know if I'm going too fast. If you want to review a previous slide, you can type it in the chat. This diagram that is on the slide is a diagram of the EPR indication system. Just an example. So here we have a turbine engine, and in this diagram we have the PT2 probe, which is near our inlet of the engine, and you have the PT7 probe, which is near the exhaust of our engine. You have your EPR transducer and wiring connection to the cockpit gauge, which gives us our reading. So pretty simple diagram. Pretty simple system, just a few facts to keep in mind there. And your EPR rating, well, it goes based off manufacturer for the engine. So those limits are going to be according to the manufacturer. Here we have another diagram, turbine system engine. Turbine engine indicating system. So it says thrust engine pressure ratio EPR, the ratio of jet pipe or exhaust duct pressure to compressor inlet pressure. So in this diagram, it's saying that this specific diagram is saying that the exhaust pressure is compared to the compressor inlet pressure. So More of this information is in turbines class. This is just kind of for reference. I don't know who or if any of you have been through turbines class, so I don't expect you to be able to rattle off the compressor probe numbers or stuff like that. But the best thing to know as far as our engine indicating system for engine pressure ratio is the inlet and outlet temperature, the inlet and exhaust temperature, okay? I know that this slide is probably a little hard to see on the video, so I wrote a little like key over here. So this just goes from the front, this just goes from the front of the turbine engine to the back of the turbine engine, and it's giving an example of where all of the pressure and temperature probes would be. So out here, it has a PT0, which basically means ambient air. So that's in this this top note here. So we have ambient air, and how that would be measured or written about in a manual, you will see P0 or T0 or PT0. That stands for pressure, temperature, and the probe number is 0. So that's our, and that's usually measured by the aircraft, not the engine. The engine doesn't measure ambient air because we measure inlet and outlet air. So then you would have PT1. There's a faint little arrow here. PT1 will be somewhere in this area at the beginning of the engine, the very front of the engine. It's going to measure the air coming into the inlet. Okay, so here we have PT1, inlet air. And then all of the rest in between go back for the turbine engine. You are going to go from your low pressure compressor and low pressure turbine, which could be PT2. Often you're going to see it as PT2. You also have here's your low pressure turbine, low pressure compressor, low pressure turbine, and it goes back. So we have PT2, PT3, PT4, PT5, PT6, and those are all stations at where pressure and temperature can be measured for your high pressure and low pressure turbines and compressors. That's all stuff that you'll get into in turbines class. So you don't really need to know that, but I hope that you're seeing the pattern of the pressure and temperature probes, because that's what we care about in the indicating system. Okay, so from the front of the engine, you're going to go from 1 all the way back. And our outlet temperature, or our exhaust gas temperature, in here is PT7 on this diagram, exhaust P7, T7 pressure temperature. It also has a PT8 on this diagram for reference of your propelling nozzle exhaust temperature and pressure. So, in this diagram, we have PT1 is measuring our inlet temperature, and PT7 is measuring our exhaust temperature for that engine. So just an idea for you guys to understand, there is a rhyme and reason to the numbers of the probes. You guys will hear, you know, what's the pressure temperature reading at PT2 or PT7, PT6, and it's not just random numbers. There is a reason why they're numbered that way. Another good diagram, this is kind of a block diagram for engine pressure ratio indicating system. Gives you your pressure ratio indicator right there on the pilot's instrument panel. You have, it also shows you, this has an example of a PT2 line, and this shows you where your PT2 probe might be on a certain engine. So this diagram has the front of the engine facing this way. Don't get confused with the last diagram, which had the front of the engine facing the other way. So just as an example, in this diagram, we would have your ice detection and vent holes on your forward nose cone here. And in this area with your inlet, you would have your PT2 probe measuring your inlet air pressure and temperature. And then all the way back here, you have a PT7 probe measuring your exhaust pressure and temperature. And it says here 6 places. So it's going to vary by engine how many probes are on this PT7 probe. In this diagram, it's saying that that means it has 6 probes. So it's taking a temperature in 6 equally spaced areas at the exhaust of that engine. And then here's your wiring for all of those readings. So your PT2 is wired, and you have this connection and disconnection port all the way up to where it shows you where the exhaust pressure line would go into your instrument for a reading, and your inlet pressure line goes into your instrument for a reading. Again, differential reading, and this is your electrical signal that's being sent to the face of your instrument. Another good diagram, I found a lot of good pictures for EPR. This is showing you the difference between, we have an analog EPR instrument and we have a digital EPR instrument, and then your engine pressure ratio transducer. Remember, we said the transducer or transmitter will transmit that mechanical reading to a electrical signal in order to display those on either a computer or your analog reading. Okay, and next we'll talk about fuel pressure indication. So fuel pressure indication indicates metered fuel pressure fitted to fuel injection systems. Typically uses a transmitter to convert electrical signal to the cockpit. So similar to the EPR indicating system, has that transmitter, because we don't necessarily want to run a fuel line into the cockpit where all the pilots and co-pilots are. That's not exactly people's favorite thing to do nowadays. So they came up with the system of converting that mechanical reading with the fuel pressure into an electrical reading to send that to a display in the cockpit. In the fuel pressure indicating system, a sensing mechanism that is used typically as part of a a sensing mechanism that is used is typically part of a transmitter device that uses electricity to send a signal to the indicator in the cockpit. So what that sentence means is the sensing remember the sensing mechanisms that we've gone over in the beginning of the term? We talked about board-on tubes, we talked about electrical sensors, we talked about diaphragms, bellows. So whatever sensing mechanism is used to read this, directly read this fuel pressure indication is typically included in the fuel pressure transmitter, so that it can include that sensing mechanism and then convert that mechanical energy into an electrical signal so that they don't have to run a fuel line into the cockpit. Okay, so we have a transmitter. You'll hear in your testing, like in your written and verbal and OMP tests for your AMT license, in that process, you'll hear them talk about a receiver. We have a transmitter and it's sending this signal to a receiver. So what's the receiver? Well, the receiver is your indicator or instrument. That's what's receiving your signal. So don't get confused by different verbiage that might be on a quiz or a test somewhere. Okay, what about gravity-fed fuel systems? Do gravity-fed fuel systems have fuel pumps? Do gravity-fed fuel systems have fuel pressure? So sometimes indications monitoring the fuel flow rate are used instead of fuel pressure. Gravity-fed fuel systems may use fuel flow meters rather than pressure meters. Gravity-fed fuel systems often do include fuel pumps. They're not typically used because the fuel is gravity-fed, such as in our Cessna 172 has a gravity-fed fuel system, and you will get into more details about the fuel system in the fuels class. All we care about is the indicating system for the fuel pressure. So gravity-fed systems do have pumps. Usually they're just for redundancy, in case they need, in case they have some type of emergency where the fuel is blocked or where the fuel isn't flowing in that gravity-fed system. So they do have pumps and primers for redundancy in different aircraft. So gravity-fed systems, do they use a fuel pressure meter? You will see gravity-fed systems use a fuel flow meter. So that will show the quantity of fuel flowing to your engine and to your system. You'll see that in your gauge, whereas the fuel pump type system will use a fuel pressure indicating system. Here's an example of a fuel pressure instrument. Okay, so we have our green range, which is the range that we want to operate in. And then we have our red range, which is the range, max and min. We don't want to be below this, and we don't want to be above this, or else there's a problem. I do have a pretty interesting video about this guy taking apart a fuel flow sensor, transmitter, transducer. There's a lot of different names, but all of them just mean they are converting that mechanical energy to an electrical signal to send to the cockpit. Once I'm done with the slides today, if we have time, we'll probably watch it. The guy in the video is kind of he's a little slow. He takes a long time to take apart this fuel flow sensor, but I think it's interesting. You guys will not get to see in this class the internal workings of a fuel flow sensor, so I do think it's an interesting worthwhile video. This is a handy diagram that you guys can refer to. There is another diagram following this for metered and unmetered fuel pressure in a Cessna. I would have to go back and check the manual to see which Cessna it's out of, but so this is a little more complicated than the diagrams we had in the EPR system, but there might be a better picture in the 8083, a little bit more simple. But you have your metered fuel pressure here measured in PSI. You have your unmetered fuel pressure here measured in PSI, and then it gives you the whole system. You have your fuel pump over here, and then you have your fuel manifold and valve assembly over here, all the way to your fuel injector nozzles. So that's something that you guys can look at. Gives a good schematic of the fuel system. And the same, another diagram. You have your unmetered fuel pressure measured in PSI and metered fuel pressure measured in PSI. So these diagrams are going to be good for you guys to look at in accordance with or in conjunction with the mock-up, the fuel pressure indicator mock-up that we're using in the lab. It will give you kind of a two-dimensional image of the routing of that system. Hydraulic pressure. Our hydraulic pressure indicating system. Our hydraulic system is commonly used for different things on different aircrafts. It can be used to raise and lower landing gear, operate flight controls, apply brakes, and more operations varying by aircraft. Hydraulic pressure. We usually have indications located at 2 locations on planes that have hydraulic pressure. Typically, it'll be located, there will be an indication in the cockpit, and then there will usually be an indication at or near the hydraulic system servicing point on the airframe. So if we have a hydraulic system that operates certain components, we have a servicing point to check that system. And that system needs to be operated at certain pressures. So we have a indicating point in the cockpit and an indicating point at the servicing port. Indicators used by maintenance personnel for servicing are almost always direct reading board-on-tube type gauges. Cockpit gauges usually have system pressure transmitted from sensors or computers electrically for indication. Okay, so the gauges that we are worried about, the gauges that we will typically see most often, we'll see both gauges because we'll be in the cockpit doing functional checks and running engines or stuff like that. But we will see the servicing port gauges more often than, or at least in my experience, I've always seen the servicing port gauges more often than I've seen the cockpit gauges, because we deal with those really often when servicing the aircraft and checking to make sure that that system is operating correctly. Hydraulic pressure, which operating mechanism would typically be found in a hydraulic pressure gauge? Okay, so what operating mechanism am I talking about? So when I say operating mechanism, operating device, stuff like that, we're talking about what device is internal to that gauge. What is sending the reading? So the answer to that is a board-on-tube type, okay? And this is a question directly out of your ASA test book. And so on the previous slide, I mentioned you can have both, right? The cockpit gauges usually have system pressure transmitted from sensors or computers electrically for indication, and that's if you have an digital system. The cockpit gauges can have analog gauges as well, but the gauges that are at the servicing point are almost always direct reading board-on-tube type gauges. Okay, so that's where that question and answer come from. That's directly from your ASA. So that is what the FAA wants you to know about hydraulic pressure indication instruments. What mechanism would you typically find in a hydraulic pressure gauge internal to the gauge? The answer is board-on-tube type. Okay, vacuum pressure. Okay, vacuum pressure. Gyro pressure gauge, vacuum gauge, or suction gauge, these are all terms for the same gauge used to monitor the vacuum developed in the system that actuates the air-driven gyroscopic flight instruments. Okay, so some interchangeable terms there. You will hear it labeled as any of these names: a gyro pressure gauge, vacuum gauge, suction gauge. Those are all operated by vacuum pressure. Air is pulled through the instruments, causing the gyroscopes to spin. That's how gyroscopes operate with vacuum pressure. Vacuum is a differential pressure. Remember, we have some different types of pressure. We have differential, we have absolute, we have standard, and we have gauge pressure. Those are our 4 types of pressure that we talk about in instrumentation of aircraft. Pressure is compared to atmospheric pressure through the use of a sealed diaphragm or a capsule. So that is our sensing mechanism in a vacuum pressure gauge. Is often done through a diagram or a sealed diagram or a capsule. Vacuum pressure is a device usually made to open or close an electric circuit when a certain pressure is reached in a system. And I don't know if you can see that from the video, but this is a really good simple schematic for you guys to look at, just to get an idea of the vacuum pressure indicating system. I like using these types of schematics because it doesn't show too much. In this class, we're just worried about instrumentation and the system that uses. We're not necessarily worried about the entire aircraft or engine, because those are related to other classes. So we have our engine-driven vacuum pump. Our vacuum pump has a vent line for pressure, okay? So we also have our vacuum relief valve. It has a regulating valve. Here it shows our attitude gyro indicator, our vacuum gauge, and our air filter. So we have incoming air that's filtered. We want our instruments to have clean air, especially our vacuum instruments, especially our gyro instruments, because they depend on that air so much. So we have our incoming air is filtered through our instrument air filter, is sent to the vacuum gauge, and then operates our attitude gyro indicator in this diagram. And we have our air that's sent to our relief valve. If the pressure is correct, then the relief valve stays in place, and it's kind of goes around and around, goes through the vacuum pump and back. And if the pressure ever reaches above what it's set for, then that relief valve will relieve the air. And you have your key down here. I don't know if you can see that, but this double line, such as right here for the vent, the double line represents discharge air. So in the vent line, it's discharging any unused air. The dash line, such as for the filter, is your inlet air. So like I said, we have air coming in that is filtered through our instrument air filter. You will change a lot of instrument air filters. They're due every so many hours. And then we have our the key, so it's vacuum. So standing for our vacuum. Pressure in the system, which goes, from operating our instruments to our pump, which is what keeps it pressurized. So that's a good diagram to take a look at. And we have pressure switches. Okay, so pressure switches monitor whether the pressure developed by a certain operating system is too high or too low, so that an action can take place should one of these conditions occur. Pressure and position switches are used to sense various operating conditions in order to provide feedback to the cockpit or an aircraft control system. Okay, so just a fancy way for saying that we can have pressure switches that act as pressure regulators. They send electrical signals if the pressure gets too high or too low. All of the fires in Mammoth have made my throat really dry. Okay, more about pressure switches. They can indicate fuel pressure and oil level. They're also used in the de-icing system. Those are just some examples of places that pressure switches are used in different systems. Pressure switches are designed to react to an external pressure applied to an actuator surface like a plunger, a snap disc, bellows, or diaphragm by a medium such as air, oil, water, hydraulic fluid, fuel, oxygen, or other gas, any of the stuff that we use in aviation. Pressure switches are physically connected to the operating medium by ports. So that's just another fancy way of saying pressure switches use ports to transfer whatever air, gas, or liquid is being used in that system. A pressure switch is a simple device usually made to open or close an electric circuit when a certain pressure is reached in a system. It can be manufactured so that the electric circuit is normally open and can then close when a certain pressure is sensed. It can also be manufactured that the circuit can be closed and then opened when the activation pressure is reached. So it's going to go either way. That's the point of the pressure switch. It's going to be put in a system to operate whether it wants to open when the pressure is gets at a certain point that's too high, or it can be operated to a point where it, the pressure switch closes if a certain point gets too high or low. It can go either way. So the construction of pressure switches contain a diaphragm to which the pressure being sensed is applied on one side. There's actually a good picture of this in your book, in the 8083, if you get a chance to look at it. I think it's a good picture. The opposite side of the diaphragm is connected to a mechanical switching mechanism for an electric circuit. Small fluctuations or a buildup of pressure against the diaphragm move the diaphragm, but not enough to throw the switch. Okay, so that's some simple construction of the operation of the pressure switch. When pressure meets or exceeds a present level, preset level, designed into the structure of the switch, does the diaphragm move far enough for the mechanical device on the opposite side to close the switch contacts and complete the circuit? Okay, so I'm not sure why that's written as like a question. When pressure meets, so that's, I'll correct that before I post these slides, but that is the operation of the diaphragm. It needs to move far. If it has little fluctuations, it's not going to set off that switch. It needs to move far enough to that preset limit in order to operate the switch, whether it's going to close or open that circuit. Oh, here, I think this is the picture I was talking about. So, actually, I think there's another picture that's really good in your book too. It has a picture of the diaphragm with some operating force applied against it, showing you kind of how that works. But this is a good picture too. We have our cannon plug port right here, and pressure inlet air, atmospheric pressure air, and you have your diaphragm right here that's connected to your mechanism for your contacts. So this is out of your 8083, so you can look at that. This is the internal operating details of a pressure switch. And I think this video is this is a good video on how those operate.
Start tracking any project or workflow in Java. Start tracking any project or workflow in Java. Start tracking any project or workflow in Java.
Hang on, I have like an echo going on here. So this is actually a pressure switch. I think it's from maybe an air compressor, but it still has a good description of how a pressure switch works and how the settings are set on those pressure switches. And that internal cutaway is a good diagram to see.
Hi, Chris with RC Worst here, and since our product video on the Square D pressure switches, we've received some questions on how to adjust the switch's pressure settings. So remember, before attempting any adjustments, be sure to turn off the breaker or disconnect power going to the switch or to the pump. You can find the factory preset settings inside the cover or on the box of the pump. This particular one is preset to 3050. So that would be the pump turns on at 30 PSI and off at 50. If you have a submersible pump, it's most likely going to be set to 4060 because that's more common with the submersible pumps. And you'll even find some jet pumps, usually smaller horsepower, or some centrifugals more focused on irrigation that run on a 2040 split. You'll find most pressure switches operate with a 20 PSI or 20 pound differential. Adjusting the center nut will raise or lower the range, so you could potentially increase or decrease the range of that 4060 or 3050, I'm sorry, that we're preset with. So by tightening this middle set screw, we're actually increasing or raising the pressure by whatever amount depending on the turns that we do here. This particular switch is rated about 2 to 3 PSI for every full rotation clockwise, and that would increase the pressure 2 to 3 PSI. The smaller nut on the left-hand side adjusts the differential, which actually only affects the high-end pressure. So for example, on this 3050 configuration, if I were to tighten this or go clockwise, we would be increasing the 50. So 51, 52, 53. It increases depending on the number of times that you turn it. So with this particular one, it's a lot less adjustable than the large one. And a lot of pressure switches have a range that this will work. Sometimes it's 5, 10, or 15 PSI, depending on the switch. Let's go ahead and run this pump through a cycle so you can see how the pressure switch operates. And we'll also see what's going on with the pressure gauge. So you can see the pressure's dropping. Once it hits that 30 PSI mark, the pump is going to engage, and it's going to build up to our 50 PSI and then shut off. So let's say we don't have enough pressure in the house, so we want to operate at a higher level of pressure. Let's go ahead and adjust this. And what we want to do for this example is we want to run at 60 PSI, so we want to increase this factory set switch to a 60-40 split. So when I say 2 to 3 PSI per turn, that's going to basically be 3 to 4 turns for us to increase it. So we have the breaker shut off. So now we'll get on here and do 3 turns. 1, 2, 3, and I'll actually just do 3.5, and we'll see what we get for a cycle. So the pressure's dropping. And you can see that at 3.5, we've actually dropped to 40 PSI, and then the pump shut off at 60 PSI, just as we expected. Extremely easy to change that adjustment. Now, let's say, for instance, that we want to adjust the differential, which is not necessarily something that you want to adjust unless you've got a very specific reason to do so, because like I said, it only impacts the high pressure or the shut-off pressure of the pump. So there's very few applications where you want to shorten the cycle, but we'll show you how it interacts in this particular configuration. So we'll actually back this. No, we'll leave that one alone. We're going to take this one here and we're going to turn it just 3 full turns. 1, or that's a half. 1, 2, 3. What this is going to do is give us actually a longer cycle, so the pump runs longer and also shuts off at higher than 60 psi. I would guess about 65, 64, somewhere in there, and it's because I turned it clockwise. So the pressure's falling, and we're about 40 psi. The pump continues to build pressure, and about 66 actually. So that was about, what was that, 3.5 turns, or 3 turns, I believe, that I did on that one. So 3 turns upped it about 5, 6 psi. So it's almost 2 psi per turn.
Now for a quick recap. Here are some reasons why you may want to adjust your pressure switch settings. For example, your surface pump is located at a lower elevation than the home or area that you need to supply water to. Raising the range will compensate for the pressure loss of the hill. Have more pressure in the shower or faucets. If your switch is not operating like it once was, here are a few tips and things that you can check. Sediment.
Okay. So I'm going to stop it there because it talks more about residential pressure specifics that we aren't really concerned about. But I thought that was a good cutaway diagram of a pressure sensor switch. Let's see where I'm here. Okay, so the internal operations of a pressure sensor switch. And we will begin talking about our temperature sensing instruments. We have our EGT, exhaust gas temperature indicating system. The exhaust gas temperature system shows whether the combustion chamber is running too hot or too cold, too lean or too rich. Gives us a conditional reading of the internal of the engine. An EGT probe is installed about 4 inches from, oops, that's actually a CHT probe. Oh, no, that's right. An EGT probe is installed about 4 inches from the cylinder head on the exhaust system. So on a reciprocating engine, this probe is installed near the cylinder head on the exhaust system. Primarily, well, the EGT can be used for troubleshooting field management issues. We can determine if the engine is running too lean or too rich and adjust accordingly for the fuel management. So EGT probe is a thermocouple type reading. The thermocouple has a junction of 2 dissimilar metals. These dissimilar metals on an EGT probe are going to be chromel and alumel. That is what a thermocouple uses. A thermocouple is heated and produces a voltage which is proportional to the temperature at the junction of the metals. The gauge is a millivolt reader calibrated in degrees Celsius or Fahrenheit. So this thermocouple instrument is actually a pretty interesting instrument. It takes the reading of those dissimilar metals and converts it into a voltage reading. And from that voltage reading, we have a indicator that's calibrated in a degree, and that's what it gives us, is a degree reading. You'll see when we measure these probes, we'll use in the manuals what's typically called out for is a megger or a millivolt reader in order to test these thermocouple probes to make sure that they're in the correct operating range. I've seen a lot of thermocouple probes where you'll have where it'll not read at all. Usually, if there's something wrong with it, you'll get like they'll call it a dead thermocouple because it usually won't read certain voltage. It'll read too low, and that's when you know that it needs to be changed out. Okay, so this is another question directly from your ASA test guide. Measuring by using what type of temperature measuring device? So EGT measuring is accomplished by using what type of temperature measuring device? Chromel, alumel, thermocouples. Okay, so when you're asked that question, that's what it's talking about. It wants to know what type of device is used to measure this temperature measurement, and it's a thermocouple, and that thermocouple is made out of chromel and alumel dissimilar metals. We also have CHT, our cylinder head temp. It has a similar operation to the EGT. The CHT probe measures a voltage proportional to the temperature and sends a signal to the cockpit indicator. The CHT probe is typically installed on the hottest cylinder head, and that is determined by the manufacturer. Okay, so we are just getting into our temperature sensing instruments, so we will be covering the EGT, the CHT, we'll go over oil temperature. So for today, we're going to stick with the EGT, was our thermocouple reading. Okay, and we had some information about how that operates, what we can use it for as far as troubleshooting, where it's installed. And what type of reading it has. The EGT is a junction of two dissimilar metals, right? Those metals being what? Go ahead and type in the chat. Okay, so the two metals that are used in an EGT probe for that reading. Okay, I think it takes a while for the chat to catch up. But we talked about those and how it operates. The thermocouple is heated and produces a voltage which is proportional to the temperature at the junction of the metals. So that's how that signal is sent. Yes, chromel, alumel. And we will do that in lab too. You guys will be measuring some thermocouples to see what the process of that inspection entails. Okay, and your ASA question here. Measure EGT is measured by using what type of temperature measuring device? Alumel and chromel thermocouples. And your CHT. Similar operation to your EGT. CHT probe measures a voltage proportional to temperature and sends that signal to the cockpit indicator. The CHT probe is typically installed on the hottest cylinder head determined by the manufacturer. Your textbook, the 8083 FAA handbook, doesn't really have many diagrams for these systems. So what I would advise is looking into some of the aircraft manuals that we have and looking at some schematics for those indicating systems and really getting some more information on how they work and tracing those systems. Okay, and I think that's it for the slides today. Next week, we are going to cover more of the temperature measuring systems. We are also going to cover, what else are we going to cover? I want to finish up the temperature measuring systems and talk about directional instruments. We'll start talking about some directional instruments, and hopefully by Thursday, we can finish up those temperature sensing instruments, directional instruments, and then discuss on the following Tuesday, the pedostatic system. Because the following Thursday, we are going to have the midterm. So I will discuss that more with you guys in lab. I'll also make a post about that on Canvas, and I will let you guys know the subject material that will be covered in the midterm. All the stuff that it's going to be everything that we've covered up to next Tuesday. So a week from today, anything that we cover on, we're going to take the midterm first. Well, actually, I guess the midterm will be on Canvas, so it will be available to you guys. So anything from the beginning of the semester all the way through next Tuesday will be game on the midterm. And I'll discuss that more with you guys in lab when everybody is present. Other than that, anybody that is live here on the chat, do you guys have any questions, or would you like to see any of the previous slides again? Go ahead and type and let me know. If not, I'm going to, let's see. I'm going to play this video of the guy taking apart the fuel pressure sensor. But I'm probably going to fast forward through some of it because he takes a really long time. And then you guys can feel free to watch it if you would like. It's not required. I'm not going to require it. There's nothing on your quiz today about the fuel pressure sensor in that video. So, but while I put it on, if you guys have any, okay, Ken, I see you said, no, you don't have any questions. So that's it. If anybody else has any questions, you can type in the chat while I play the video of the fuel pressure sensor disassembly. And like I said, I'll discuss more about midterm and stuff like that in the lab. I will open up the lecture quiz today. Will be open at 6, so don't forget to take that. Okay.
Hello guys, I'm Chris Bowden. Welcome to the Geek Group. In this week's Equipment Autopsy, we are taking apart a transmitter. Now, this isn't like the kind of transmitter like you think, like this radio net. This is a piece of avionics equipment. It's for in probably a very large airplane. This is the transmitter side for the how much gas you're using per rate of time gauge. It's kind of like a gas gauge, but instead of measuring how much fuel is in your tank, it's how much you're using. If you look here, you can see this is the transmitter. The receiver would be the gauge in the cockpit. And this transmits the rate of flow for fuel in a range of 50 to 45,000 pounds per hour, which is a hell of a lot of fuel. So it's kind of cool. Now, this is our third attempt at making this video because this thing has been a bit of a pain. So instead of watching me take out all the bolts, some of them are already out. We kind of, it's like when Julia Child just reaches down and, hey, it didn't take me 6 hours to cook that turkey, it's done. This is that kind of thing. So there were 4 bolts here. It wasn't anything terribly exciting. We didn't miss one. No, we got it. It's there. So let's take a look at what we've got just from the outside. Here's the cover. There's 2 of these plates on top. There's one here. Now inside we've got a little 2-pin socket, held in place with safety wire that holds the bolts. Safety wire is something you'll see a lot in danger places. You see them a lot in aircraft and stuff like that. It's a way of making sure that the screw is never going to come out on its own. Because if you have like, like this thing's coming out on the side of a jet engine or something, so it's a lot of vibration and there's heat and expansion and then it cools off and it contracts and everything's moving around. You really don't want your screws to just start falling out. So they use safety wire to keep them in. And we'll take a look at that real quick. I'll remove these screws. I'll do it over on this panel because this one's still screwed in. It's the same thing. This plug has 3 pins on it, but you can see the safety wire on the top. Now I'll just cut this like that, and we'll just cut the wire right off. Now we'll pull that wire out, and you can see, let's screw it there. Wow, this is kind of manky. Slide the wire right out. Now pull this bolt out, which is more than a little bit oxidized. I'll turn it around like that so you can see. Now, if we look really close, you can see inside